This is a lecture on Gauss-Jordan elimination. It's really going to be 2 lectures because otherwise it would be just too long. So what is Gauss-Jordan elimination? It's a method for solving systems of linear equations. Right? If you have just 2 equations and 2 unknowns, then you know how to use the method of addition and the method of substitution, or the method of elimination and the method of substitution. And that's pretty easy to do. When you get more than 2 equations, the whole process gets incredibly messy and sometimes intractable. So what is done is to take those system of equations, write them in matrix form, and the matrix and these Gauss-Jordan elimination rules will allow you to find the solution, and you won't have those a million equations all over the page. It really maintains a form, and it gives you a structure for solving them. Also, it's very easy to implement on a computer. First thing I want to do is go over the way to solve linear equations when you have only 2 unknowns, because it is from these rules, especially the rules for elimination, from those rules that Gauss-Jordan is built. So if you don't understand the connection, you might feel that they just came from out of nowhere, which they didn't. So I'm going to let this be the system of equations, 2 equations and 2 unknowns. I'm going to solve it first by substitution. I asked you to do that on homework so you recall what this means to have a system of equations. So when I substitute, I have to rearrange one equation to isolate the variable. In this case, I'll isolate x. Once x is isolated, I substitute. Let me clear the screen for a second. So I have x here, and I substitute it for x in this equation because I used this equation to isolate the x. Then I put the x back in the other equation. Now, when I do that, I get this equation right here, which is an equation for y only. It's a linear equation in y. I solve it by isolating y, and I end up with a few steps as y equals 5. Then I take this value of y equals 5 and I put it back into either one of the equations. Actually, you should put it into both and it better work out. You better get the same answer. So I put it back into these equations. In this case, I put it into the first one. Well, I used the one right here, the second one, and I substitute the 5 into it, and I get 3, and that's my equation. That's my value for x. If I had used this equation and put the 5 in for y here, I would get 3 again. You better get the same in either equation, so that doesn't matter. So here's my solution: x of 3, y of 5. And that was by the method of substitution. Here's what the solution looks like graphically. We have 2 equations. Here was 2x plus 4y equals 26, the first equation. Here was the second equation, minus x plus 5y equals 7. I draw both of those lines. They're straight lines. The point where they intersect, right here, that's the solution. Now I want to use the method of elimination. And to do that, again, here's my original equations. I multiply the second equation by 2, so I get a new second equation here. Then I add the 2 equations together. The x's, of course, I get 0 x's, put that there for a reason, but that drops out, of course. And I have 8y equals 40. I divide both sides by y, of course, by 8, of course, and I get y equals 5. So what were the rules I had here? I multiplied an equation by a number. Then I added the equations together. And essentially what I did here was multiply this equation by 1 over 8, or I divided by 8. So I'm multiplying an entire equation by a number, and then I'm adding the equations together. Those are the rules which come over to Gauss-Jordan. Here's a list of them again. You can multiply or divide both sides of an equation by the same number. You can't divide by 0, of course, and you don't want to multiply by 0, of course, or you wipe the whole equation out and then you can't use it. The second thing you could do, if it's to your advantage, is you can switch the order of equations. The first equation doesn't have to be first on the list. They're just a group of equations, and order of the equation is not important. The third thing you can do is add or subtract multiples of equations from each other. And we're using matrices now to make this method work for more than 2 equations and 2 unknowns. For the first example, though, because it's easy to do. I'm going to use the same equations again, and I'm going to use the Gauss-Jordan method here so you can see it without having too big of a matrix to worry about. So here's my original equations. 2x plus 4 equals 26 and minus x plus 2y equals 7. I write this as a matrix equation. Recall what this is. The first matrix is called the coefficient matrix. That's the coefficient matrix, is right there. That 2 by 2. The vector of unknowns has the x and y, and the solution vector is on after the equal sign. So I write that into matrix form as a matrix equation. Remember, if I don't have a variable listed in one equation, I have to include it as a 0 in the coefficient matrix. Here are the tools of the Gauss-Jordan elimination method, and they're exactly the same as for the algebraic elimination method. You can multiply or divide both sides of an equation by the same number. You can switch the order of equations, and you can add or subtract multiples of the equations together. When doing all of these multiplying, dividing, adding, and subtracting of the equations, nothing happens to the x and y variables. They stay the same. We actually don't need them, and as long as we maintain the column structure in the matrix, then we can just eliminate them from the picture. All we really care about are the matrix of coefficient and the solution vector, and what we do is we put them together and create what's called the augmented matrix. Here's the augmented matrix, and to get this, I took all these terms from the coefficient matrix and I combined them with the solution vector, and x and y don't have to be there. As long as I keep the columns in the same order, I don't need to explicitly include x and y at this time. So this is the augmented matrix, and I'm going to work with that. I'm going to give you another example showing the augmented matrix. Here is a system of equations, 3 equations and 3 unknowns. From this I can write the matrix equation. Here is my matrix of coefficients, here's my vector of unknowns, and here's my solution vector. Both of those, the coefficient matrix and the solution vector, are combined to form the augmented matrix. The goal of Gauss-Jordan is to apply those rules that we mentioned before to turn the coefficient matrix into the identity matrix. Let's say that you did that somehow. The coefficient matrix right here is the identity matrix. Then we have, of course, this solution vector here. Now that's my augmented matrix. I'm going to take and pull it apart and put it back into the matrix equation, right, and multiply through it. I'll tell you what my original equations would be. It would be 1x plus 0y plus 0z is 25. The second would be 0x plus 1y plus 0z is 10. And then there should have been a plus in there. I don't know what happened. 0x plus 0y plus 1z is 14. In other words, if I have this, if the coefficient matrix is the identity matrix, then x equals 25, y equals 10, and z equals 14. And that's the goal of Gauss-Jordan, is to turn the coefficient matrix into the identity matrix.